So today let's look at how to take the integrals of odd powers of sine and cosine. And the method we're going to do is this. So the first thing we're going to do is split off all but one of the sine or cosine. I'll show what I mean by that. Second, we're going to use the Pythagorean identities to rewrite the even power Third thing, we'll use U substitution. And from there, we'll just evaluate whatever it takes after that, whether it's an indefinite integral finishing off by going back and putting in plus c, or whether it is a definite integral and evaluating the limits of integration. So split off all but one of the sines or cosines. So if I had something like the integral of sine to the 2k plus 1 x dx, so k being some integer, then this is the same thing as sine to the 2k of x times sine of x dx. Similarly, if I had the integral of the cosine to some odd power, 2k plus 1 x dx, then I can split off as the integral of the cosine to the 2k of x times the cosine of x dx. And now, if you recall, we know that sine squared x equals 1 minus cosine squared x, Pythagorean identity, and cosine squared x equals 1 minus sine squared x. So, over here, this sine to the 2k x is the same thing as sine squared x to the k times sine x dx. And I can rewrite this sine squared as 1 minus cosine squared. 1 minus cosine squared x all to the k times sine x dx. Similarly here, this cosine to the 2kx is going to be integral of cosine squared x all to the k times cosine x dx. And I can rewrite this cosine squared as 1 minus sine squared all to the k times cosine x dx. And I won't finish it all the way off in here in this general form. I'll show you some specific examples. But in here, if I were to let u equal cosine of x, when I do the u substitution, this sine of x is going to cancel. And over here, if I were to let u equal sine of x, when I do u substitution, this cosine is going to cancel. So that's what happens. That's how this works. Let's take a look at 3 examples and see how it can be applied. So evaluate the integral of sine to the 5th alpha d alpha. So I see that this is the same thing as integral of sine to the 4th alpha times sine of alpha d alpha. I'm going to change the sine to the 4th into something in terms of cosine. So that's going to be the same as, and I'll write this step here. I'm not going to write it in the further examples. I wouldn't do it if I were you, because you can probably jump over it. But just to make it clear what's happening, sine to the fourth alpha is sine squared alpha squared. And from there, I can rewrite sine squared alpha as 1 minus cosine squared. So I have 1 minus cosine squared alpha squared times sine of alpha d alpha. And now we're going to go through and do a little bit of u substitution. So I will let u equal cosine alpha. I know that's going to work because I have this sine alpha that I can cancel out with. So I know that du equals negative sine alpha d alpha. And d alpha, which is what I'm going to need to replace here, I'll replace this thing with u. D alpha is going to equal du divided by negative sine of alpha. And so, when I come up here, this is going to equal the integral of 1 minus u squared squared. I'll leave the sine in here for a little bit, times the sine of alpha, and I'll replace the d alpha with du over negative sine alpha. I see that the sine alphas cancel. The negative I'm going to bring to the front, so I get negative integral. I'll expand this of 1 minus 2u squared plus u to the fourth. That's just expanding this. Du. And when I take the antiderivative of this, I get a negative. I have the antiderivative of 1 du is u. The antiderivative of 2u squared is 2u cubed over 3. The antiderivative of u to the fourth is u to the fifth over 5. And I'll put a plus c here at the end. So distribute through the negative, and I get negative u plus 2u cubed over 3 minus u to the 5 over 5 plus c. And finally, so notice I sort of went to this green work here with this sort of u space, u world here. I need to get back to where we started because my problem does not have u's, it has alphas in it. So I remember u is cosine of alpha. So my final answer will be negative cosine alpha plus 2 cosine cubed alpha over 3 minus cosine to the fifth alpha over 5 plus c. Okay, so that was an example with just a single odd power of sine. What if I have something like this, where I have an odd power of one of them and an even power of the other? Well, I start the same exact way. So I'm going to split off one of these cosines. So I get that will equal the integral of cosine squared beta times cosine beta times sine squared beta d beta. And again, I'm going to sort of skip some of these steps now. We saw it all shown out in the previous. So cosine squared is the same as 1 minus sine squared. And I have cosine beta times sine squared beta d beta. And now, same thing. If I let u equal sine of beta, then notice I have a single cosine beta. So this will be replaced by u, this will be replaced by u, but the single cosine beta is going to cancel out. So du equals cosine beta d beta. And I'm going to need to replace this d beta, so I'll solve for that. D beta is equal to du over cosine beta by dividing both sides by cosine. And so now when I rewrite this, I get the integral of 1 minus u squared. I'll leave the cosine in for a brief amount of time. Cosine of beta. This sine is the same thing as u, so sine squared gives me a u squared here. D beta I will replace with du over cosine beta. And now the cosine betas cancel out for us. I don't have a negative that needs to come in the front here because the derivative of sine was positive cosine, and so I can rewrite this as the integral of 1 minus u squared times u squared du. And I don't need to expand this, but I do want to distribute the u squared so I can take this antiderivative easily. And so I get the antiderivative of u squared minus u to the fourth du. Antiderivative of u squared is u cubed over 3. Antiderivative of u to the fourth is u to the fifth over 5. And I'll have a plus c. And I didn't have u's in the original problem. I had sines and cosines of beta. So the final thing to do here is to replace the u with sine beta, because that's what u equals. So I will get this equal to sine cubed beta over 3 minus sine to the fifth beta over 5 plus c. So these two problems were indefinite integrals. We ended up with a plus c. What happens if we have a definite integral? Well, pretty much the same thing. In this case, I also had odd powers of both, and it doesn't actually matter which one you choose to split up. I could either split up sine or split up cosine, but it would be a mistake to try something like this, to try to rewrite this as sine squared times sine times cosine squared times cosine, and then sort of split these up, because you're going to end up with things that will not cancel and use substitution. So that is not the right idea. Pick one or the other. So I guess I will pick cosine, just for a reason that I'm going to avoid a negative when I do that, but it doesn't really matter. And so I will rewrite this as the integral from 0 to pi over 2 of sine cubed theta times cosine squared theta times cosine theta d theta. And I will rewrite this cosine squared as 1 minus sine squared. So 0 to pi over 2 of sine cubed theta times 1 minus sine squared theta times cosine theta d theta. And now when I look at this, I notice that if I let u equal sine, I'll be able to replace this and this with u, and this cosine here is going to cancel. So I will let u equal sine theta du equals cosine theta d theta. And this is why I chose cosine to split up, because I'll have a sine, and when I let u equal sine, I get a positive cosine. It makes my life maybe a little bit easier. And I'll solve this for d theta, and I'll get that d theta equals du over cosine theta. Now, one option at this point is I could just go ahead and drop the limits, do an indefinite integral to get the antiderivative, and then go back into sines or cosines and put the limits back in. But I prefer this method. So these are theta values. We have theta equal to 0 and theta equal to pi over 2. When theta is equal to 0, though, u will equal the sine of 0, and sine of 0 is 1. No, it's not. Sine of 0 is 0, sorry. When theta equals pi over 2, if I'm trying to change this all into u's, then u will equal the sine of that theta value, sine of pi over 2. And the sine of pi over 2 is 1. So if I want to rewrite this and never come back to sines or cosines, just deal with the u's, which is probably going to be easiest, then I need to change the limits as well. So this all gets me the integral from 0 to 1, because we're talking about u's now, not thetas, of, replace this sign with a u, so u cubed, replace this sign with a u, 1 minus u squared. I'll leave the cosine here for a brief second, and replace the d theta with du over cosine theta. The cosine thetas cancel. I will distribute the u cubed through, so I get integral from 0 to 1 of u cubed minus u to the 5th du. And I'll take the antiderivative. Antiderivative of u cubed is u to the 4th over 4. The antiderivative of u to the 5th is u to the 6th over 6. I will evaluate this from 0 to 1. When I put in the 1, I get 1 to the 4th, which is 1 over 4. When I put in 1 here, I get 1 to the 6th, which is 1 over 6. And it should be obvious, but when I put in 0, I get 0 over 4 minus 0 over 6, which is 0. And a common denominator here, so least common denominator will be 12. So 1/4 is the same as 3/12, multiplying top and bottom by 3. 1/6 is the same as 2/12, multiplying numerator and denominator by 2. And 3/12 minus 2/12 is 1/12. Okay, feel free to put any questions in the comments, and I will move on to even powers of sine and cosine tomorrow.